I have the pleasure to introduce the first talk by Professor Laurent Cohen from the Sept in Paris. It's on geodesic methods for interactive image segmentation.
Okay. Thank you, Hakim. So I will present, as you said, geodesic methods for interactive image segmentation. Can you hear me well? Or, yeah. Okay. So first I will give some background on geodesic path, fast marching front propagation, and then we'll see extension of this to more recent kind of metrics like until Finsler metric, and two recent applications of the new Finsler metrics to segmentation with curvature penalization and region-based segmentation. So we introduced path of minimal energy about 20 years ago in order to find the global minimum for active contours. So active contours are a way, an evolving curve that finds contours in images, and by minimizing energy composed of feature-based term and smoothing term. So it is known that active contours are, since they are evolving, they are often stopped by a local minimum, and so we simplified the active contours in order to find to be able to interpret the active contours as a minimal length curve, and so thus find the global minimum. So in order to do that, we had to remove the curvature term that was in the active contour, and so at the end of the talk, we'll show that recently we were able to reintroduce this curvature term. So basically the problem is to find a path of minimal energy, where the energy is the integral of P of CNRS ds, where CNRS is a curve drawn on an image domain, and P is a feature potential. P is defined on the image domain. It can be related, as here, to the gray level, where you're looking for a vessel that is darker than the rest. So the potential can be an increasing function of the gray level. And when you minimize P, the curve locates on darker region. And so the input from the user is a starting point P1 and an endpoint P2. And the output is the minimal path, the global minimum of the integral of P among all paths that join P1 and P2. So this is not limited to linear structure, but it can be also used for contours, where the potential P, as in usual active contours, is based on the gradient, then the path will follow the contours of a region. So the idea was to interpret the energy as a length. It means that if E is defined like this, where P is assumed to be positive, and that it corresponds to the interesting features in the image, then you define what is interpreted as a weighted distance map to any point P in the image domain. So P1 being the starting point here, P in any point in the image domain, then UP1 of P is defined as the minimal energy among all paths that join P1 and P. And this, as I said, is if you interpret P as a weight at a local metric for the length of the curve, then this is the weighted length, and this is the minimal weighted length among all paths that join P1 and P. And so it can be interpreted as the weighted length from weighted distance from P1 to P. And so this, as we'll see, can be solved using UP1, this solution of Iconal equation. And when you solve it numerically, then you find a minimal path by simple gradient descent along UP1. Okay, so it can be shown that UP1 satisfies the so-called Iconal equation, norm of gradient UP1 equals P, with boundary condition UP1 of P1 is 0, and the classical case where P is equal to 1, then integral of P is the length of the curve, and the minimal length is correspond to the segment and it corresponds to the Euclidean distance. So it's known that the Euclidean distance satisfies gradient d equals 1. In general, this is interpreted as being a weighted distance where the, as I said, p is a metric. So p is a constant metric. No, I mean not constant, but depending only on the location of the of x. So the second step, once we solve numerically Eichhorn equation, is to make gradient descent, which can be seen as solving ordinary differential equation starting from the endpoint P2 and joining P1. Since, in fact, this equation is satisfied by UP1, P is positive, so UP1 has no local minimum except from the starting point P1, for which it is 0. And so gradient descent will always connect P2 to the starting point P1, and it can be seen that the trajectory followed by this ordinary differential equation is a minimal TAF, is minimum geodesic according to this distance. Okay, so here is some example. In fact, so here you see an original image. So it is an easy example to understand how things go. So first thing is to extract the potential, and then you give P1 and P2, and you will find a path that minimizes this potential. And the first thing is to solve the Eichhorn equation using the fast marching algorithm, which correspond to solving this equation by increasing values of U1, and this starts at P1, and it corresponds to a front propagation from P1 till it reaches the whole domain. And then when you have solved this, starting from P2, you make a gradient descent. So this is here the graph of UP1, and starting from P2, you make a gradient descent on this function UP1, and the path followed by this gradient descent corresponds to a minimal geodesic between P1 and P2. So here is another example on a real image. So here you give the starting point, descent point, and you find the minimal geodesic. So here you don't need to solve the fast marching on the whole domain, but you can stop when you will reach the endpoint, because since it is a gradient descent and U is obtained by increasing values, you have all the information needed. So it is very fast, because the fast marching is itself fast, but here you have to solve it on a very small portion of the image domain. Okay, so this is basic minimal geodesic, and so it was extended in the past years to different spaces and different metrics. And one interesting space to look at is the 2D plus radius space, which enables you to consider a tubular model. In fact, as I shown in the first slide, this is very well adapted to tubular structure like vessels, and a tubular structure can be described completely by its center line and local radius, which can be itself represented as a 3D curve, which here, if I consider a space x, y, r, where x and y are the 2D space of the image domain, and r is a radius dimension, then a point x, y, r in this image, in this space, represent in the image domain a circle or disk of center x, y, and radius r. Then a curve drawn in this 3D space corresponds to a collection of disks in this 2D space, where the projection of the 3D curve to the 2D domain corresponds to the center line, and the envelope of all these disks will correspond to the two red lines here, to the boundary of a tubular structure. So a curve in this 3D space, 2D plus radius, corresponds to a center line plus boundary description. And so the nice thing is that you can design a metric in this 2D plus radius space that allows you to find exactly I mean, to make the center line locate in the center line of a tubular structure and the boundary as well. So here is an example. Here you give a starting point and end point, and in the solving this minimization in 2D plus radius will give you the center line plus the boundary of the structure. So it gives you a complete description of the tubular structure. So here are examples in the retina images where we have been working the match. And here you give two examples, two pairs of points. So this point connects to this one and this one connected to this one. And here is the result where the red curve here is the center line and the blue curve are the boundaries of these vessels. Okay, so here you see how the radius dependent energy looks like in a very simple shape, a U shape here. And the radius dependent energy means that for each value of the radius r, you have a potential P of xy, which is defined. And what you see here is the darker blue correspond to the smaller values. And what you see here, I don't have time to explain exactly what happens, but for the good value of r, the potential is smallest at the center line here of U. So solving here the minimal path between 2 points will give you center line plus boundary. Now what happens very often in these methods of minimal geodesics is that you can take a shortest path, which is a shortcut. That is, if you give this starting and end point here, then the minimization, the global minimization prefers to choose a short path with a high value of potential rather than a very long path with small values of potential. And so this is the problem that is often encountered. And so here this problem can be solved in different ways, but one way it can be solved is the next thing that we see is to take into account the local orientation of the path. So here, so far, what you minimize along the path is some value which depends only on the location of the path. But here you see that the path is here should go in this direction and it goes in the orthogonal direction. So if you penalize the path according to prior orientation, then you are able to find the good path. And this is what we're going to see next, is to define a metric that is anisotropic, which means a metric that depends locally on orientation as well as location. So here it means that you extend what we did before to potential depending both on location and also orientation. The orientation of the path, so it's the tangent to the path, C prime. And the nice thing is that you are able to extend what we did for isotropic to anisotropic, where here in the relevant way to define this anisotropy is a Riemannian metric, where H here is the tensor field defined on the image domain, and so here you define this local metric, which means that H here usually has one preferred direction and the orthogonal direction is the more penalized. And according to the orientation of C prime, you'll have a different cost. So this is something that we introduced long ago with Gabriel. So hello, Gabriel. It's an occasion to say hello. And so this can be shown to defining U the same way as before to be the minimal length along all paths between P1 and P. Then it can be shown that UP1, the anisotropic weighted distance, will satisfy this iconal equation where H is the tensor field defined on the image domain, and still with UP1 of P1 equals 0. So now, in order to find a geodesic from P2 to P1, you make, instead of gradient descent, the direction of descent is deviated by H minus 1. So these formulas are in the special case where H here, the local tensor metric, is proportional to an identity. It means that it has no preferred orientation, and you can see that the two equations that we had before here and here comes back exactly to the iconic equation we had at the beginning for isotropic matrix. So what it means is that if you define the tensor field H at each point, it can be decomposed into eigen values, eigenvector direction. And if you assume that lambda 1 is positive and lambda 2 is larger than lambda 1, then locally you can represent the unit ball according to H. And this corresponds to an ellipse which has as a long axis the one corresponding to lambda 1 to E1, which means that the representation of this unit ball is useful to visualize the preferred orientation, because the longer here is the axis, it means the smaller lambda 1 is relatively to lambda 2. So when an ellipse is very elongated, it means that lambda 1 is much smaller than lambda 2, which means that there is a much larger anisotropy, which means that here you have a preferred orientation where in this direction lambda E1 you will have a much smaller length than if you go in the other direction. It means that the long axis of the ellipse here is a preferred orientation for the geodesics, that the geodesics will tend to follow the orientation of E1. So here is an example of how it behaves according to the anisotropy, where you define a metric which depends on the two orientations which are shown here. So here you have the set of ellipses that visualize the metric. So here at each point, the orientation, preferred orientation, is circular orientation, and radial is the most penalized. So it means that the preferred curves here would be, the geodesic would be half circles. And so if you get a starting point here, P1 and point P2, and the metric here is obtained with different values of lambda 1 and lambda 2, here W1, W2, the more you increase the penalization, the more you increase the anisotropy, then the more the minimal path will align with a half circle. So here in green you have the half circle, the precise half circle, and in what looks like pink here is the minimal geodesic. So here in the case W1 and W2 equal, which means you have isotropic constant metric, then the minimal path here corresponds to a straight line. So it corresponds to Euclidean descent, so it corresponds to a straight line. So when you increase W2, so you increase penalization of the radial orientation, and so the curve tends to align with circular orientation. And so here it is exactly above the half circle. So this shows how anisotropy can influence the orientation of the minimal geodesic. And so in a few years ago, this was difficult to use because of the classical fast marching method was not very efficient when the anisotropy is large, and till a few years ago we had to make a different algorithm which was more evolving U here, and so it was not very, it was efficient numerically, but it took much more time. So this was still Jean-Marie Mirbeau extended fast marching method to anisotropic metric using a set of local neighborhood, discrete neighborhood that can adapt to the local anisotropy. And this very efficient method allowed to still have very fast solution of the of the iconal equation, even in the case of high anisotropy. And this enables to, as an example, to illustrate what we had before with the case of the U shape. So if you define the anisotropic metric according to the prior you can find on the local orientation in the image, then you can influence the local, the minimal geodesic in order to follow the prior orientation. It means that when you analyze and extract the geometry of the image, we are allowed to find a prior orientation, and this is something that is very common in vessel segmentation, and there are many different ways to do that. For example, based on the Hessian matrix, I mean we're taking the eigenvalues and eigenvectors of Hessian matrix, or what is called optimally oriented flux, which is another way to find locally the best orientation if the image has a preferred orientation. And so this is what we show here, the optimally oriented flux, where you see that according to the scale, so here the radius is interpreted as a scale, and for each scale you represent the ellipses of this metric obtained by optimally oriented flux, where you can see, or maybe you cannot see, that here in the middle you have elongated vertical ellipses, while elsewhere you have ellipses that look like circles. So it means that you have no preferred orientation in the background, but when you are at the very center here, you have a preferred orientation which is vertical, which means that if you use with what we used before, without orientation led to this minimal path here it will have a high penalization of the orientation here, and it will prefer to follow the preferred orientation from the oriented flux, and that maybe you see better here, and it will follow the U shape. So this now can be extended to applied to a real image. So here you have a real image of vessel, and the first thing, as I said, is to extract the local geometry, and locally it looks like that. And you see that along the vessels you have these ellipses that are more elongated, and then given a starting point and an end point, you get this 2D plus radius minimal geodesic according to anisotropic metric. And this can apply as well to road images which look like vessel, are as well tubular shapes. And this can be extended to 3D plus radius space, where you find here the 3D center line plus boundary of vessels in 3D images. And here is a second example. So you see here a starting point, and here different endpoints, and you see that the radius can evolve along the path. Okay, so let's now go to more recent work and more recent extension to the more general metric called Finsler metric. And so it corresponds to a metric depending both on location and orientation, and we'll see two examples of application of this Finsler metric. So, so in fact, the first goal here was to reintroduce the curvature that was lost in the first minimal path, the curvature that was present in the active contours, and the way it is reintroduced is using an orientation lifted metric, which means that what we do here first I will say the general case of Finsler metric. So you have a metric where the length of a curve gamma is defined as the integral of f gamma of gamma prime of t, which means this is a general formulation of a metric depending both on the location and the orientation. Gamma prime here corresponds to the orientation of the curve. And then the same way as we did before, you define for a starting point P And then for any x, point x in the image domain, you define u of x is the minimum length among all paths that join p to x. And then the general formulation of the iconal equation satisfied by this here is f x star of gradient u equals 1, where f x star is defined as the conjugate transform here. And this is a general iconal equation. And then once you solve numerically this equation, you get the minimal geodesic according to this metric during this gradient descent here, which is according to f star. And here the condition, the Finsler metric that will be useful in what follows, I mean, in different cases we use, is an extension of the anisotropic metric we just used. So here you have a term which is correspond to the Riemannian metric, where M is a tensor field defined on the image domain. And you add this term here, W scalar U, where U is the orientation of the curve, and W is a field of orientation of vectors in the image domain. So in order to have a positive metric everywhere, you have a condition here on M and W, which is this condition. And whenever this condition is satisfied for all x in the image domain, then this definition leads to a positive metric, and you can do what we said before, so solving this iconal equation and solving this minimal path extraction, and finding global minimum for this minimization. So where this term here, which is added to what we had before, is introduce something that may be surprising at first, which means that here, if you take the orientation u and minus u, you don't have the same metric, which means the path that goes this direction and the path that goes this direction will not be have the local length, the same local length. So at first it may look special, because it means as well that the minimal path joining P1 and P2 will not be the same as the one starting from P2 and going to P1. So it may look odd at first, but if you say that you're going to go up a mountain or down a mountain, it doesn't have the same cost for you, and so it makes sense to say that such a metric makes sense in some way. So, but you're going to see that it has also some usefulness for finding contours in images. So once you have defined this Finsler framework, and this correspondence is called the Randers metric, then you are able to solve the minimization of elastica. So finding the curve minimizing this energy, where k is a local curvature of the curve, and this can be transformed in a problem where you find the minimal length curve according to a Finsler metric. And this is done the following way. So if gamma here is a curve, then classic calculus says that if you define theta of t is the local orientation, so it means that gamma prime over norm of gamma prime is exactly cos theta sin theta. So this means simply that theta is the orientation of the curve. Then it is well known that the curvature can be obtained by derivation of d theta, which is obtained here, where t here is any parametrization of the curve. It's not necessarily arc length. Then if you replace here in this expression of elastica, you change variables s to t, and then you replace kappa, the curvature, by its value here. You find here this integral over t of norm of gamma prime plus alpha theta prime square over gamma prime, and this itself can be interpreted as a Finsler metric, which means that here we are going to define a Finsler metric on a 3D space, which is composed of the 2D space of the image domain plus an orientation space. So it means we make an orientation lift on the image domain and define the space as being defined as a curve gamma here is composed of a 2D curve, a curve defined on the 2D domain, plus the an orientation function. So this is a general curve, so it's defined in the 2D plus orientation space, or called orientation lifting. And then if you define v theta as the vector of orientation theta, then the definition of the Finsler metric here is exactly what appears here in this integral. So gamma prime plus alpha theta prime over gamma prime, which means here gamma and theta are not necessarily the related in the general case. Here gamma is any curve composed in the 2D plus orientation space, where theta is not necessarily the orientation of the curve gamma. And here the way it is, this Finsler metric is defined is just exactly the way that this will be the metric if gamma prime is proportional with v theta. So here is, if the theta here is the same as the orientation of the curve, then the metric will be this. If not, it will be infinite. And this Finsler metric allows you to have equivalence between minimizing the Finsler metric in this 2D plus orientation space and minimizing here the elastica in the 2D space. Now, I will not go into details, but this is very, brutal definition of a metric, because you have some values somewhere and infinite very close. So this cannot be solved directly, but it has to be, in fact, the way we solve it is to approximate f gamma infinite by a set of f gamma lambda, where when lambda tends to infinity, the metric tends to this metric. So it is solved, numerically solved a little more smoothly, and it allows you to find the global minimum of this elastica between 2 points. Okay, so this is what I said. And for image processing, the elastica is interesting if you add here some coefficient alpha and beta depending on image features. So here, so if alpha and beta are depending, for example, on the gradient of the image or on grade level of the image, then you get here exactly what corresponds to the active contours, where you have both a feature potential based on the image values and a smoothing term based on curvature. So here are some simple example or illustration of what you can do with this metric. And so here you have the potential P, which is smaller on this H shape, and using a classical minimal path with isotropic metric here, giving a starting point here and an endpoint here, will give the shortest path that goes on the gray region of this image, which correspond here to follow this 8. So now if you add this curvature penalization using the elastica minimization, then here you see that you have a high curvature, and it will prefer going this way to join the other point, even if the potential here is smaller. I mean, here it is darker than here, and so here the penalization of curvature will prefer this path here. Now, as I mentioned earlier, if you go from P1 to P2, or if you go from P2 to P1, it's not the same. And the nice thing here is that if you change P1 and P2 here, what you get is this path, which is unexpected, but you go here on the other part of this H shape, which means that by concatenation of path between P1 and P2 and P2 and P1, you get a closed curve that covers a complete H shape here. And this will be useful for finding closed contour in images. So here is our examples in real images, natural images, where the potential is based on the color gradient. And you see here minimal geodesic according to Finsler metric, in where here you give starting point, end point in these different images. And you see that you get very smooth curves that follow the contours, the expected contours. So these images are maybe easy or not, but here another example in medical images where you have vessels. Here you have vessels here, and what happens often when you use isotropic or anisotropic metric is that you have this phenomenon that you can combine different vessels in order to find the minimum, global minimum, which means that if you give a start point here and end point here, the three paths that join to the starting point here, they follow vessels, but they can be a combination of different vessels that cross. And so here at the beginning, what you see here for some potential region, instead of going this way, it jumps here to the neighbor vessel and follows this way. But it can also happen in different ways. So here you see here that you start from this vessel and then you go to another vessel. So when you add here the curvature penalty, then you get smoother curves, and you see that you follow exactly the real vessels. So you don't have jumps between different vessels. And this can be illustrated in these different images, that what you get with different kind of metric, isotropic or anisotropic or radius lifted, you get always this kind of jumps between two vessels in order to minimize the metric. While here, where you have curvature penalization, it behaves much better, and usually you get a curve that follows a real vessel. Okay, so it's the same. So now let's go to real contours, and you can find a closed contour as a set of minimal geodesics between these points. So given here a set of points, you give this set of points, and there's an easy way to connect this point automatically. So it means that you don't give them in a given order, but you can connect the first point you make. You'll connect it to the first point, the closest point according to this geodesic distance. And so the first point it meets will be Q2 here, and so you get this first path. Then Q2, you start fast marching evolution from Q2, and the first point met is Q3, etc. Q4, and then you link Q4 to Q1, and you get here a set of Finsler paths here that make a closed contour, and this closed contour corresponds to the boundary of the image, so it looks easy here. But what you can see in these different examples is that here you see the feature potential, the image features are very complex. You have edges everywhere, and using different metrics like isotropic or anisotropic or another kind of metric here, what you see is that using this path between points, given points, you get very bad results in these cases. While adding the curvature penalization gets the very good contour, which correspond to smooth contours here. So you see that in all these examples, the minimal path between 2 points will take other interesting contours, but which are much more chaotic. So you see another examples. like the example we had at the beginning here, you see that it is not so easy using other kind of metrics without curvature penalization. Okay, so another examples, and this is an examples where you take only 2 points now, where you have here P1 and P2, and you have the path joining P1 and P2 and the path joining P2 and P1, which are not the same, and combine to form the complete closed contour in these 4 cases here. Okay, so this was the first application of Finsler metric to reintroduce curvature penalization in minimal length path. Now, a second recent application of this Finsler metric is to include region-based segmentation in minimal geodesics. So in this way, it means that all along we've been able to express as minimal length paths, and which means that we have access to global minimization to all kinds of active contour terms that were previously used, which means that of course the potential term, but also the curvature term, and now the region-based term. Okay, and so the region-based term corresponds to an integral over region B here of a feature f, which, for example, you can think about Chan-Visi term. So you have a function f of x defined everywhere in the image domain. So you can always express this as like this, the integral on inside the region of feature potential. So this is a region term, and so the idea here is to transform this region term into a Finsler geodesic path. So to find to transform this region-based energy in a curve-based energy. So here, and this way, the region B will be found through a set of minimal paths according to this Finsler metric. So the idea when to transform a region-based term in a curve-based term, you immediately think about that to the divergence theorem, or different names to this, but to transform a region-based to curve-based integral. So let's first formulate the problem. Here you find you're looking for a shape minimizing the region-based functional f, which so there's a problem here. I am a little confused because you don't see u here. So on my screen you see a tubular region. So, so you can imagine a tubular region in gray that surrounds the black curve here. So here, in fact, in order to be able to transform this integral, you will formulate the problem as finding a shape B star in red inside a tubular region around the initial curve B. And then you will find this red curve as a set of minimal paths, which will be global minimum according to the Finsler metric. So yeah, so I don't know how to show you this, but anyway, the idea here is that once you have limited here the problem to a tubular shape U around this curve, then the problem can be transformed to find a new V here field here, such that divergence of this field here is exactly alpha f key u, where the characteristic function of u, where you can rewrite this region-based energy here can be rewrote as, so I said here that you will limit to the region U, and so this can be limited by adding this term characteristic function of U, so the region U, and this itself, if alpha f times the characteristic of U is equal to the divergence of some field, then you can apply the divergence theorem to transform this region integral to a curved integral. So here this is replaced by this, and so it means that you know a vector field V such that this takes place. So it is called here V orthogonal in order here when you make the divergence theorem here, you make appear after you make a rotation to make appear exactly V here. So here at the end of the equation here, what you get here is a Finsler metric where you have this term in the Randers metric V scalar gamma prime. So this is a term that appeared earlier in the Finsler metric, and so everything is going well here. If you are arrived to this metric, you are able to solve this minimization using a Finsler metric. So now the problem is how to find this vector field V, and in fact first this is what I said orally, that this is a Finsler metric, and in order to be able to minimize it, you have to check for the fact that it is positive, and then it can be minimized. So here, in order to find V, the V field here, then what you do is to solve this equation with constraint minimization here, and in this way I don't have time to explain here, but we have a way to find it, V such that this equation holds, and as well that we can transform it in order to have this condition of positivity satisfied. And in this way, we can use this minimization of Finsler geodesic in order to find region-based minimization. So it assumes here that you have some points that are some initial curve that is on the image, then you sample a few points on this curve, and then for each of these points you find the global minimum of the Finsler metric between pairs of points here. So you get a new curve, and for this new curve, once again you don't see it, but you have to imagine a tubular shape around this red curve now, and you resample it, and you update the Finsler path. So you iterate this process a few times, and then it's stabilized to find the global minimum of this. So here you see an example on a real image. So you have an initial curve which is a circle. You sample it with these 4 red points, and so here you have a region-based term in order to find inside here. So first, so you evolve these geodesics. So here you see 4 geodesics, and then you see the next step, and then the final step. You see that you are already on the boundary, and then you are stabilized in these 4 steps. So you have here the result, which correspond to minimization of the region-based term. And here a second example where the interaction assumes that the user gives these 3 points and these 3 points will not move. So in the first case, the initialization was an initial curve, which can evolve. I mean, you don't impose any points. So here, in this case, you assume that you impose these 3 points to be fixed. And so what evolves here is the geodesic between these 3 pairs of points. So here you see the different iterations. So what changes in different iteration is the tubular boundary where you solve the minimization. But at the end, this tubular boundary is okay, it doesn't change, And this stabilizes here to this minimization. And just in time, I conclude to say that we introduce minimally interactive tools for segmentation, where the user usually provides one initial point or different endpoints. And this is based on fast and efficient propagation algorithms. And we were able to include in the models orientation, scale, curvature, and region-based information. And this leads to possible application to segmentation of natural images, as well as using a set of geodesic paths. Okay. So thank you.
Thank you very much, Laurent. Other questions, comments, remarks?
You know the work of Thomas Schönemann for minimizing the geodesic active control on a product graph. There's a construction where you have a product graph of orientations and image nodes. So is there any similarity between them?
I didn't hear the name.
Thomas Schönemann.
No.
It's computing shortest path, but standard extra, so discrete forms.
No, I don't think so.
I think it
No, I'm interested in getting this.
So for the very first model, so you are essentially using finding the topographical distance and the topographic path between the 2 points. So they are ready software to compute the topographic distance for a given function. So your method then compare with that one, are there some relation or?
What do you mean topographic? Not really
distance, you give a surface and you every 2 points you find the path such that the variation along these paths are smallest. That's exactly.
It's not exactly that. No.
It's not exactly.
No. What I showed is the graph of the distance map. It's not related to the distance along the surface.
It's not geodesically showed it along the surface. The topographic distance, you have any 2 points. You find the arbitrary paths and see how much variation along these paths. And the smallest variation is called the topographic distance between 2 points.
Okay. So
it seems that you are exactly finding the same thing. And they are ready software to compute the topographic distance.
okay. But the advantage is that you are sure to get global minimum in a very fast way. So.
How do you think this could be extended for cases when you can't identify all endpoints, like it's infeasible, like a tree is so detailed and you want to extract the whole tree? So there are tons of, like detailed vessel tree in 3D, and so you can't click on all endpoints. What do you do?
Oh, so I didn't have time to present it, but I can show. We propose different ways to do that. Yeah, we have the so-called key point method, where you introduce automatically key points that explore a tree structure. So you don't know anything here. These points are completely automatically introduced, and you find here at the end the center line of the tree structure and the boundary of the tree structure.
What if you make a mistake? Like, for example, the automatic method doesn't put it in the right place.
Well, we never made any mistakes.
We have to go ahead with the next talk. We can postpone additional questions to the break. Thank you very much again.